Welcome to the first of two videos over Chapter 3. The first video will contain the overview, what we're going to cover in this chapter, as well as how to name compounds. The second video will contain the different math that we'll need to use in Chapter 3 with a variety of masses of those compounds. So, what are we going to learn in Chapter 3? Well, we're going to learn compounds. What they are, how they form, how to name them. The second thing we're going to learn is naming compounds. We're going to learn to name the three different types of compounds: ionic compounds, molecular compounds, as well as acids. We're also going to learn a variety of different mass calculations. Things like how to calculate formula mass or molecular weight, how to calculate mass percentages, how to use mass or percentages to determine a formula of a compound. And then we're going to finish the chapter with a brief introduction on how to balance equations. And this is going to be very important in Chapter 4, 5, and 6. And so we're just going to briefly introduce how to balance equations, some of the rules for balancing equations in this chapter. So, we are going to learn how to name the three different types of compounds in this chapter: ionic compounds, molecular compounds, and acids. Ionic compounds are formed when a metal binds to a nonmetal. We are very familiar with an ionic compound already in table salt. Sodium chloride, a metal with a nonmetal. Now, the way ionic compounds are formed is when a metal and a nonmetal get together. And when a metal and a nonmetal get together, the metal becomes a cation, positively charged, and a chlorine, or the nonmetal, becomes an anion, or negatively charged. And the reason why we get an ionic bond that binds a metal and a nonmetal together is to neutralize that charge. This is why when you put salt in water, that they can dissolve. So, how do we name an ionic compound? Well, we take the name of the metal and we don't change it. We take the root of the nonmetal and we add "ide" to it. So in the case of sodium chloride, we have sodium, the name of the metal, we don't change it, and then we take the root of the nonmetal, which the nonmetal in this case is chlorine, so it would be CHLOR, that's the root, and we're going to add "ide," sodium chloride. The more practice that we have with these different compounds, the better that we will get. So let's look at a couple examples, because there is a variety of different types of ionic compounds. So let's look at this. MgBr. Metal, nonmetal. So we know we're dealing with an ionic compound. Mg is magnesium. So Br is bromine. But since it is an ionic compound, we'll take the root and add IDE. So magnesium bromide. Let's look at another one. Cesium iodide. So you will have to be able to either name the compound when you're given the molecular formula. So this is the molecular formula. It tells you how many molecules or what molecules are combined in a compound. You will also have to be able to take the name and write the molecular formula. So here we have cesium iodide. We're probably familiar with iodide, or its more common name is iodine, as I. Cesium is in the first column of your periodic table, and it's CS. So, the more practice you guys have with these different compounds, the easier these will become. Let's look at another form of ionic compounds. Let's look at iron. So, iron is what's known as a transition metal. Transition metals can adopt multiple what's known as charge states. In the next slide, we will cover how do we calculate those charge states. If a metal, like iron, has different charge states, we have to add something to the naming. And so here we know we have chloride, because we know Cl is chloride, and we know Fe is iron. But since iron is a transition metal, it occurs in the metals in the middle of the periodic table, we have to add another bit of nomenclature. So iron can adopt either a +2 state or a +3 state. And so we have to distinguish between the two when we name it. In this case, it's iron 3 chloride. And I know you're thinking, well, how in the world did we know that that was iron 3? In the next slide, we'll look up the periodic table, and I will show you how we can use that to help us determine the little subscripts on these compounds. Let's look at another example of naming a compound. Mg3N2. So we've seen Mg before. Magnesium. N is nitrogen, but we'll drop the ogen and add ide. So we have magnesium nitride. Notice what I do not do with the subscripts. I do not turn them into words and put them before either the metal or the nonmetal. So it's not trimagnesium dinitride. In ionic compounds, we just put the name of the metal and the root of the nonmetal with an ide next to it. Now, how about this compound? There are some ionic compounds that are surrounded by water. Those are known as hydrates. Magnesium sulfate heptahydrate is a commonly used ionic compound in the form of Epsom salt. Here's another one. So let's name the ionic compound first before we go to name that hydrate. So we have barium, which is Ba, chloride, but now there's an extra part. Whenever we have an H2O around an ionic compound, we call it a hydrate. And so here is where we need to learn the numerical words. So for 6, that is hexahydrate. So hydrates are named. You name the ionic compound. You put hydrate at the end with the number of waters right before that. So again, there's problems in the back of your book that we can work on. We'll work on them in class so that you can name a compound both from the formula to the words or from the words to the formula. So then, how do we know the subscripts? How do we know in this compound magnesium needs to have a 3 and nitrogen needs to have a 2? We look at the periodic table and we can find different trends and different charge states. That's why we need the subscripts, is to get rid of the overall charge. So, how do we know? Starting with lithium and below, these are known as alkali metals, or alkaline. These metals are very reactive. These metals always adopt a +1 charge. So if you see a lithium, sodium, potassium, rubidium, cesium, you know that that will always be a +1 charge. The next row over are alkali earth metals. These always adopt a +2 charge, right? So if you see beryllium, magnesium, calcium, strontium, then you know that those always adopt a +2 charge. The metals in here are known as transition metals. These adopt multiple charge states. Like we saw with iron, it can be a +2 or a +3. Starting with fluorine and on down, so fluorine, chlorine, bromine, iodine, these are known as halogens. These are nonmetals. They usually adopt a -1 charge. Here's oxygen. So oxygen and down usually adopt a -2 charge. And then nitrogen and down a -3. And that's where we'll stop with the negative charges. Right? And so we can use these rules to help us name some compounds. So let's look at a compound. Let's look at potassium oxide. So we're going to look at potassium oxide. Is this drawn correctly? Well, let's check. Potassium is here, and we know it adopts a +1 charge. Oxygen is here, but we know that it adopts a -2 charge. So right now, oxygen is at -2, potassium is at +1. Do we have a neutral charge on this ionic compound? The answer is no, because oxygen has -2, potassium has +1. So how can we neutralize this charge? We can put a 2 on the potassium, and so we can have potassium oxide. So now this goes into a +2 because we have 2 potassiums, The oxygen is still at -2, and now we are neutral. Let's look at another example. Let's look at copper chloride. Let's name this compound copper chloride. Copper can take two states, either a +2 or a +3. Or, excuse me, a +1 or a +2. So here's copper. It is a transition metal. I said it could take a +1 or a +2. Copper chloride, let's see where chlorine is. Chlorine is over here. Chlorine always takes a -1 charge. So we know chlorine takes a -1. Copper can either be a +1 or a +2. We have two chlorines. So we know that the total charge on the chlorine is a -2. So to neutralize this charge, we need the +2 state. So the name for this molecule is copper 2 chloride. The more practice we get, the better we will become. So, how do we then name molecular compounds? Well, molecular compounds are different than ionic compounds because they are actually bonded together through the sharing of electrons. It is a nonmetal with a nonmetal. So let's look at an example that we have seen in class before. We said this was carbon monoxide. So, carbon monoxide. How do we name molecular compounds? We take the name of compound 1, or of element 1, and we keep it the same, just like we did with the ionic compounds. So in this case it's going to be carbon. And then what we do is we take the root of second element and add "ide." But we don't stop there. We add a numerical prefix before each one. And so I know what you guys are thinking. Shouldn't then CO be monocarbon monoxide? Whenever we have a mono as the very first prefix, so if we just have one element in the molecular compound, so in this case it's carbon, we do not have to put mono in front of it. It is assumed when you just say carbon that we're talking about one carbon. So let's look at a couple examples of this. So, the first element is nitrogen. The second element is iodine, but again we're going to take the root and we're going to add "ide" to it. So then we have to find if we need to add a prefix. And we need to add a prefix before iodide, and the prefix for 3 is tri. There's multiple examples in your book with prefixes that you can look over and study, along with table 3.4. Table 3.4 will be a very important table for us to memorize in this class about polyatomic ions, how some compounds have more than one atom and they have an overall charge to them. So things like nitrate, nitrite, hydroxide, acetate, when we talk about acids, those will come up. So let's look at another example. Tetraphosphorus, decasulfide. That's a mouthful. Tetraphosphorus, decasulfide. So here we have two prefixes, which would suggest that in both parts of our molecular compound we need subscripts. But we know we have phosphorus and sulfur. So now we just have to make sure we have the right numbers. Phosphorus, it's tetra, that means 4. Sulfide is deca, and that means 10. So tetraphosphorus decasulfide, P4S10. The more practice we have with molecular compounds, the better that we will get at naming them. The last thing that we are going to learn to name is acids. There are two different types of acids that we're going to see. The first type we're going to look at is H followed by some element, usually a nonmetal. The way we name these acids is you always have hydro followed by the element root. So again, we're talking about roots. But then we add an ic. Instead of an ide, we're adding an ic. And then we add acid to it. So it's hydro something acid. Let's look at an example. HI. So, hydro. So we know there's going to be at least hydro and acid. So every time you see an H at the start of a compound, you should always think acid. And so there's always going to be acid at the end. So you'll at least get that. Now, I, we said was iodine. There's the root of iodine. And so then we add IC. So this is hydroiodic acid. So how about this one? Hydrobromic acid. So we know it's an acid, so it's going to start with an H. Bromic is the root of bromine. And so there is hydrobromic acid, HBr. Hydrogens, just like we saw in the periodic table, go with the alkali metals. Hydrogen is always +1. Bromine is always -1 because it's a halogen. So we don't need any subscripts because the charges neutralize. But there are other types of acids that use those polyatomic ions found on table 3.4. And so here we need to slightly modify the way we name these acids. Let's look at a couple of examples. Besides having nitrogens and oxygens the same, these are acids because they both start with a hydrogen. So we know at the end of both of their names, they will have acid. Now, if we went to table 3.4 and we looked what NO2 is, NO2 is nitrite. NO3 is nitrate. So how are we going to name these? Well, just like everything else we named, we take the root. So there's the root of both of those. Both nitrate and nitrite have the same root. Then we look at the endings of each of these polyatomic ions. If it is ITE, we turn it into OUS. So ITE, ite, goes to us. 8, or ATE, goes to ic. So we have nitrous acid, or we have nitric acid. We do not put the hydro in front when we're talking about polyatomic ions. So we don't need to put hydronitrous acid. By changing these two endings of the words, it is assumed that we're talking about an acid. So this is why table 3.4 is very important. Because not only does it tell you how to name these things, but it also tells you the charge. Because we need to know the charge. So the charges of both NO2 and NO3 are -1. And since hydrogen is a +1, this is a valid molecular formula because all the charges are equal. So finally, how do we know whether we're naming an ionic compound, a molecular compound, or an acid? It all starts with the first element. If the first element is a metal, we are naming an ionic compound. If the first element is a nonmetal, we're naming a molecular compound. If the first element is a hydrogen, we are then naming an acid. And so as long as we know these, we can then work on how to name things right when we see them. And the more practice that we get, the better we'll be.